Not the same photo.
Start 37, start.
Welcome. So today we have Pre-Ph.D. seminar by Parisee, Shirke. He started working with the Professor Deepak Bhattacharya, and he was working, and then when Deepak moved out of Viva, the Deepak became his guide. I'm part of our RAC, so now.
The title of my thesis was initially proposed to be an investigation of polarized emission from accreting binary extra pulsars, but depending on the kind of work which was done over the past few years, there will be a slight change in the title. Polarized is replaced by beam emission, with the focus being on the pulsar beam, and I've interchanged accreting and binary, so it will now be binary accreting extra pulsars. X-ray pulsars are some of the brightest sources in the X-ray sky. There are two kinds of X-ray pulsars. Rotation-powered pulsars that are seen in the X-rays are typically newborn X-ray pulsars like the crab. My thesis will focus on accretion-powered X-ray pulsars. The diagram on the left, I think, is the closest description I've been able to find so far to give you a premise of what my thesis will be talking about. These are typically found in binary systems where the compact star accretes matter from its optical companion. The matter is obstructed at the boundary of the magnetosphere and it gets funneled onto the polar caps of the neutron star. The gravitational potential energy of the infalling matter, which is lost, gets converted into thermal X-rays, which are radiated away. Because of the presence of a strong magnetic field, this is not an isotopic emission. The radiation is strongly beamed along a preferential direction. This can be along the direction of the magnetic field, but this can also be perpendicular to the direction of the magnetic field. This is a long-standing pencil versus fan beam degeneracy issue, which seems quite fundamental to our understanding of pulsars, but has not yet been resolved. Several telescopes have been launched from the 1970s to study such systems, most of them focusing on the timing and spectroscopy, with technological advancements making it possible to have higher resolution measurements. Currently, most of the X-ray telescopes which will go up now, because of technological advancements, will carry an X-ray polarimeter on board. The X-ray polarimetry window has been closed for a long time, mostly because of technological limitations and because it's a photon-intensive process. which is what makes primary accreting X-ray pulsars prime targets for such observations because of the presence of a strong magnetic field. The first chapter of my thesis will try to model the pulse profile that we would expect to see from such systems, focusing first on the anisotropic effects, which is the directionality of the beam. Any arbitrary orientation can be encountered by an observer looking at the night sky. So we try to see what possible directions of rotation axis, direction of magnetic axis, and the observer's direction of line of sight will be taken into consideration. For this, we use model beaming functions which are available, which give you the photon intensity as a function of the emission angle. The emission angle can vary from 0 to 90 as measured from the direction of the magnetic axis. To the left, you have such model beaming functions which have been put forth by Lazarus and Nagel after having performed radiative transfer in model pulsar atmospheres. This is one example, but there are 4 that I have worked with. This one is for pencil beam specifically, but they are also available for fan beam and for 2 different values of optical depth. So I will call them shallow and deep geometries. On the y-axis, if you see, the intensity is multiplied by a cosine factor to introduce a limb darkening effect. So it's more signature of a slab or pencil. On the right, I have tried to get a deeper understanding of the photon intensities that we're dealing with by replotting some of the data which is available from this plot to try to visualize the radiation map as a function of the photon energy and the emission angle available. Suitably replotting this plot can, on one side reproduce the beaming function, but 2 can also yield the spectra which I've appended to the thesis. These are the 3 main equations which I will speak about for the numerical simulator. The first one tries to model the pulsar rotation and take the beaming function to the observed pulse profile. I came across this equation, which is a very exact equation that takes into consideration the spherical trigonometry of a pulsar and tries to use the direction of the rotation and magnetic axis as an input, allows the pulsar to rotate, and then directly gives you the direction along which the observer will view the emission, which is modeled by theta, which is given by theta. So using this theta, if you then go to the beaming function, this will be the theta over here. And then you can read off the corresponding value for the corresponding energy, which will be emitted along the observer's direction. And doing such an exercise for all possible spin phases will then lead you the pulse profile. With this, in this thesis, I have built a code that simulates such pulse profiles for any arbitrary value of inclinations, because anything is possible for the pulsars that we see in the galactic plane. I have presented 5 viewing inclinations in the thesis, but the simulator itself can handle any arbitrary inclination as an input. Each of this is possible for 4 different emission geometries: slab, pencil, shallow, deep, and for 8 discrete values of X-ray photon energy spanning the 1 to 100 X-ray observing band. 8 discrete frequencies are chosen consistent with the choice of Lazarus and other radiative transfer output for the beaming function. To this, I will present the results in a later slide. But as far as the code is concerned, to this I try to add GR effects, primarily light bending. Light bending causes the emission, which is actually directed along the observer, to be bent out of sight because the photon trajectory is slightly bent while the photons traverse in a curved space-time. So taking the gravitational field of the neutron star into consideration becomes essential if we were trying to model observations. For this, I use the second equation here. There are lots of equations available which try to approximate the path of the photon in a Schwarzschild metric, but I've gone ahead with the Belo-Borodov's approximation, and I've tried to discuss in the thesis why that suffices for our interest in this thesis. Along with it relates the emission angle of the photon, which is the initial direction of propagation along which the photon is initially ejected, to the final direction along which it asymptotes towards the observer after having traversed through the curved spacetime of the neutron star. These are related through the compactness parameter U, which is the ratio of the mass and radius of the neutron star. So the more compact the neutron star, the more bent the trajectory will be. This is accompanied with gravitational redshift. The photon, the resultant beam is reddened after having escaped the strong gravitational pull of the neutron star. This effect is increasingly pronounced for higher energy X-rays. An interesting result that I will show beforehand is the possibility of having an Einstein ring or completely flat profiles, although your source is rotating and the emission is arising from a very small region on the source. If the compactness is increased, in this case by increasing the mass and the corresponding radius of the neutron star, although the emission is initially pulsed for less compactness values, it eventually increases to a point where the flux can be completely flat as if it were a non-rotating source. But it is rotating. However, I think this remains more of a theoretical possibility, which I've mentioned here for completeness purpose, because it followed as a direct consequence of the exercise. On the right, I have shown isotropic emitters, which have also been studied simply for theoretical completeness or for comparison purpose, where the lowermost panel shows a completely flat pulse profile. If I were to input a completely isotropic and uniform injection function, as if the beam is not anisotropic at all, as if the emission were just emitted in all directions. In that case as well, you almost always end up having at least one emission region, which will be antipolar. So at least one polar cap faces towards the observer. So you almost always have constant flux from the source. The third module I've tried to have deals with surface integration. So far, the work which has been done and the radiative transfer output of the Mazars and Nagar papers, which were the model profiles, they are only applicable for point hotspots. But realistically speaking, it's never truly a point. So I've tried to incorporate a more realistic emission geometry by trying to model circular slabs on the polar caps of the neutron star, which lie flush on the neutron star surface. Such an exercise with a slab can be a cornerstone exercise that can then be extended for studying even more intricate emission geometries and make it even more realistic. So this is the third equation where I use a double integral over the emission surface. For this, I have established a polar coordinate system on the hotspot, but this is not sufficient. You have one more additional complication because it's not a single point. You will end up having slightly different emission from each infinitesimally small area element landing across your line of sight. And also you might have, because it's an extended source, some of it might go out of sight and some of it might come in. And you would also, I've tried to make this composite with gravitational bending considerations. So while also accounting for which ray trajectories will continue being bent towards you even after being out of sight. For this, I've tried to, while integrating over each infinitesimal area element, to run that integration again computationally, I tried to come up, I tried to use the geometric considerations which went into the pulsar rotation formula to apply the same to the hotspot circular area by using a clever rotation of axis. Simply doing that, which I've tried to outline in more detail in the thesis, simply doing that can help you use the same formula with more variables and make it slightly easier to account for the differential emission angle. So this was the code that was developed so far, and this here I've tried to present a comparative view. You can generate a lot of pulse profiles with the code. I've tried to present how the profiles are changing with each effect as I go on adding them. On the left, these are non-normalized profiles, so you can study the flux coming from the source. And on the right, these are normalized profiles, so only the changes in the shape or the pulse shape is of interest. On the right, you can see the red curves belong to surface integration. In the emission area is, it's already known to be a standard size of 1 kilometer square. That means about 10 to the power 10 centimeters square, and when this emission is integrated, then it naturally gives a flux boost of about 10 to the power 10 orders of magnitude, and brings the emission to the ballpark of what is typical of X-ray pulsar luminosities. Also, the top curves correspond to gravitational light bending, so when that is incorporated, you have additional flux for the same in the same flux range, along with additional contribution from the unseen side of the neutron star. On the right, you might want to compare boxes which belong to the same color. But most importantly, if you move from left to right, I've tried to keep the pulsar inclination constant. So for say a 45 degree pulsar source in the sky, the first panel here tries to reproduce the Mazaras and Nagar model pulse profiles, which are already reported in literature. This was done to test the working of the module. So once this was reproduced, I have tried to extend because these remain non-realistic profiles, simply because if you see, then the peak emission is flat. So I've tried to extend the range to the full emission range of 0 to 90. I've used the limited range because that was suitable for the radiative transfer calculations, which was their focus. My focus being the profiles themselves. So I've tried to extend the range to the full emission angle range, giving like the pointed peak profiles compared to the flat top profiles. Also, once you incorporate gravitational light bending, which is done in the third column, the profiles kindly kind of stretch out a bit, almost giving you a count. Sometimes, it's zoomed, if you see. Then this hump here kind of goes to here somewhere. In the fourth column, I have tried to add the additional contribution from the unseen face of the neutron star. You can see there is slightly additional contribution near phase 0.5. So phase 0 corresponds to when the pulsar is pointing right at you, and phase 0.5 will correspond to when it is pointing away from you. And the last one is composite with surface integration. This again slightly boosts the emission and makes it slightly even more smoother because it's extended over a larger emission area. Like I said before, there have been other emission geometries which have been realistically reported in literature. And these are more intricate in their nature. You have crescents, you have annuli. There can be regions, circular regions of different temperatures, for example. But as you can see from the diagram, the circular slab can be extended to model such geometries as well. So to proceed with the fourth chapter, if you see, then the tertiary masses present, the slide is from my topical course presentation for gravitational waves, where I had presented a paper on space-based detection of gravitational waves. This was the last slide because it was the most intricate exercise, so it was discussed in that paper. But in GW, for example, dealing with tertiary masses involves steps like accounting for the Doppler mode. So if this is your GW source and it's going around a tertiary mass, then you will have a Doppler modulation of the frequency of GW, which you will end up encountering. So they had steps like accounting for this Doppler modulation, phase calibration, accounting for the orbit of the space-based detector and such, which I noticed was very similar to what I had done in X-ray binaries in my graduate school project.
So if I understand correctly, go to previous slide. So this non-symmetric ones for your calculations, you just consider circular symmetric ones. These are future scopes you are.
Yeah. So in this case, it was an X-ray binary, which is going around. It's stellar companion, the lighthouse itself is in motion, basically, apart from the pulsations which you are receiving. Centaurus X3 has been taken as a model source, and the left panel shows astrosat raw data where you see the pulsations directly once you plot them with a suitable software. On the left, I have binned the pulse profiles at an hourly time bin. So you can see here the binary nature where the flux initially increases as the source moves towards us, and then the flux gradually resides as it moves away from us. If you fold the light curve for different time segments along the lengthy light curve, then you also see that the pulse profiles are also, the peak is slightly shifting as the source moves towards us and then recedes away as it goes away from us. So the binary nature where your source itself is in motion introduces further complexities. This I have tried to model this. We tried to model the binary orbit with this Doppler modulation, which were, these equations are similar to what I had in the gravitational wave slide. And subtracting for this orbit allows us to have some estimate about the systemic parameters, which were published in a paper in 2021 by us. Do note that there are dedicated groups that work on data analysis of X-ray binary, so they perform more high-end modeling and do more advanced work. But the point in this thesis was to try to account for the binary effect by modeling it using the Doppler modulation. So from the pulsations which I showed you, after I performed the high resolution timing analysis, I arrived at this energy resolved pulse profiles for different X-ray bands. The diminishing secondary peak is known to be a signature of a distorted magnetic dipole. In my simulations, I assume a perfect dipole. So I can proceed with the work, but realistic situations can also have distortions in the magnetic dipole, or the magnetic field can also evolve with time. Discussions on this have been provided in the thesis. I compare these profiles which I've obtained with astrosat to the simulated ones by providing the known Centaurus X3 inclination to the numerical simulator of 6520. Here I have used the 18.4 keV because the numerical simulations are for a discrete frequency energy. So I've tried to compare with 18.4, but more recently, since I was also able to incorporate gravitational redshift, thus completing the set of GR effects that need to be accounted for, I would probably need to check the right-hand panel again in the coming few days to see whether there might be any redshift changes. In the fifth chapter, I've tried to take this exercise a bit further, and I've tried to increase or vary the area of the polar caps, changing them into slightly spherical caps. So the coordinate geometry changes from polar geometry to spherical geometry. On the right, you see the surface coverage module, where the surface coverage has been allowed to span 0 to 100% of the compact stellar coverage. Note that the pulse profiles never truly flatten out because the magnetic field is still there in your pulse, and the initial function is still beamed to begin with. These are some special plots that I have that can help you see what the surface coverage is doing. On the left, the red line is for a model 1 kilometer square hotspot that I've used everywhere prior to this. And then I allow it to increase its size, and the fainter curves go towards slightly more non-pulsed side because the emission area is increasing. So there's more averaging and larger continuum. On the right, I've tried to compare this with an isotropic injection function. So just for comparison's sake, the numerical tool itself should not be coded to provide such an output. So if I change the input, the output should change. So this is simply for comparison's sake. After doing this, after having developed the variation in emission area, what I've tried to do using the Centaurus X3 energy resolved pulse profile that I have, I've tried to constrain the size of the hotspots if I can, assuming a model geometry, and try to see whether the effect of gravitational light bending is truly that significant for the case of binary accreting X-ray pulsars. This has been related through a quantity called pulse fraction, which measures the modulation that you have. It is normalized by the overall continuum, so the variation is the non-pulsed fraction is subtracted out. So this is the curve for without gravitational light bending and with. So the pulse profile clearly changes with surface coverage, as I showed you in the previous slide. Now with Centaurus X3, if I use those profiles and see how their pulse fraction is changing, then I kind of arrive at these intercepts for Centaurus X3 with gravitational light bending and without gravitational light bending. It allows me to constrain the radius. So if I use simulations without gravitational light bending, then it gives me a hotspot radius of about 12.27 for Centaurus X3. And once I incorporate light bending, the radius of the hotspot goes down to about 1.36, which is more in the ballpark of what is typically observed. This lends more weight to the importance of including these effects in the case of such compact stars. Finally, something I wanted to give voice to was the importance of pulsars.
So would you say that the effect is degenerate in the sense that if the hotspot is bigger, it degenerate to gravitational light bending in the sense that your pulse fraction is reducing both?
Yeah, but the curves don't overlap, I mean, with and without gravitational light bending, because I think the light bending itself introduces a massive change. So the variation because of the surface coverage seems less compared to the variation because of light bending. So at least from 0 to 100 surface coverage, the curves don't overlap for this case at least. Pulsars can be used to study in reverse physics itself. So here I've tried to exploit the thermal nature of the radiation, and I've tried to measure free Gaunt factors that characterize the radiation and plasma matter interaction in model pulsar atmospheres. So it's accreted plasma suspended in a very strong magnetic field and irradiated with hot thermal Bremsstrahlung X-rays. Such conditions of extreme physics are seldom reproducible in terrestrial laboratories, so pulsars are often exploited as naturally occurring rich astrophysical and physical laboratories. The presence of a magnetic field asks for the Gaunt factors to be resolved into two, a G perpendicular and a G parallel. Each of them will be a function of the energy of the X-ray photons and the strength of the magnetic field. While calculating this, I tried to develop a Gaunt factor calculator that can give me the Gaunt factor for any possible value of X-ray photons in the entire range of 1 to 100 keV, which is possible, which is your X-ray observing band, or for the full breadth of source pulsar magnetic fields, which is 10 to the power 11 to 10 to the power 13. That is the formula for computing these Gaunt factors. In Gaunt factor literature, I have come across various Gaunt factors being reported for various different physical conditions, including astrophysical applications, for example, in galaxy clusters or something, but I never really came across one which discussed Gaunt factors in the case of pulsar atmosphere, so I've tried to calculate that. The squares show the Gaunt factors which have been computed, the calculators can give you any Gaunt factor for any arbitrary value, but here I've tried to show Gaunt factors for model X-ray photon energies that have been used in the simulations before and which were used by Mazars and Nagel in their radiative transfer computations. And I've tried to sample the full band of cyclotron energies taking some model values. But that may not be essential, so I've tried to remove that constraint and I've tried to arrive at Gaunt curves which only ask you for a source pulsar magnetic field strength and can yield you the value for the entire observing band. I tried to exploit the computing power of our desktops and see if this could be extracted at a higher resolution. So this maps out the entire Gaunt functions over the entire observable range of pulsars and X-rays. Finally, in chapter 7, I again give voice to pulsars as promising laboratories for studying fundamental physics itself. irrespective of the pulsar emission mechanism. The fact that it's a highly magnetized vacuum gives rise to vacuum effects kicking in, which can produce birefringent effects that cause the outgoing X-rays to be split into an X mode and an O mode of polarization. So a new window is opening up in the X-ray polarization in the high energy sky. The bulk of the polarization in accreting binary X-ray pulsars is because of the magnetocontent scattering that takes place in the pulsars, but in the atmospheres. But even without that, because of vacuum effects, you would have had some polarization because of the presence of a very strong magnetic field. In my thesis, therefore, I've tried to give very detailed outline of the mathematical steps that you would have to account for. These algorithms are loosely available in literature because there have been people in the previous century who have tried to make some advances in this direction from a theory point of view. But now that this window is opening, there have been recent reports in literature where people are trying to come up with updated estimates. However, a lot of assumptions go into the newer modeling. So I still find the previous literature to be quite sound and solid to build upon. And I've tried to unpack some of those algorithms in their mathematical details. So chapter 7 will be simply providing mathematical steps as a proof of concept of using a Fourier discrete ordinate method where a 3D grid is used to keep track of every single photon scattering and interscattering between the O and the X modes within the pulsar atmosphere, and then trying to render the mathematical steps to more computationally suitable forms for its computation, and that will help us build a bigger tool or a software that can help decipher any X-ray polarization signals that can be detected at high resolution by upcoming telescopes. So just by knowing the degree and the angle of polarization, such a software will be in a position to directly provide the source parameters, basically. These are additional algorithms of how this can be put together.
So you mentioned the vacuum effects. Have you included that?
The vacuum effects are naturally go into these algorithms, where I speak of a vacuum factor, for example, or there was the interscatterings that take place have accounted for the vacuum effects.
So you accounted for vacuum biofrequencies while you
I have not performed the radiative transfer. I've given the algorithms, and the algorithms account for the magnetoscattering and vacuum based on their own calculations. There will be additional complications when polarization is involved. The polarization vector would have to be tracked as it is parallelly transported through a curved spacetime. Again, there are different approaches of going about this, but life gets a bit complicated. What I've tried to do from my side is try to append algorithms of how to do this to the thesis for completeness. Like I said, various people deal with this, but their entire work is based on Lazarus's work, because it seems to be the most stand its ground. As far as the span of the thesis is concerned, based from what it was planned to be and where I was able to make it, the numerical tool does account for a wide range of input parameters. So I've been able to account for different systemic configurations, as was even mentioned in the abstract, and a slab. There were additional possibilities which were included just if the initial exercises turned out to be quite simple and one could go ahead. And as far as the pencil and fan beam were concerned, I also have some lines of thought on how polarization tries to would provide a decisive blow and a conclusive decision on whether a pencil or a fan beam is being observed. But recently I've come across other lines of thoughts where you could also have alternate approaches, and they're based on the compactness parameter, for example. So that's also something to think about. And on the right, there again, direct prediction of a wide range of observables. Because of the breadth, this had to be limited to the pulse flux. The spectra and polarization would naturally follow. I've put that in the future scope for the time being, but that's slightly long-term exercises. There will be 3 main publications. This one has already been published where I dealt with SNXP, but it's not central to the thesis. The main output of the thesis is the simulator itself. And then, based on some of the output I've been recently deriving from it, there can be 2 more that discuss the physical and geometrical chapters. I mentioned the word comprehensive in the abstract. I should justify. I've tried to address all the physical effects which come into play. The physical conditions, the ones which were relevant to slabs have been incorporated, but the ones which require a wider range of accretion luminosities has been reserved as a future scope. And finally, in classes of observations, I've been able, because of the breadth, I've been able to do this for pulse profiles, light curves, but this can be, this front would have to be pushed for spectra and polarization resolved characteristics. This is the final slide, which will give you an overview of the current status. There will be 7 chapters. I'm right. 1 is remaining for me to write, and the corresponding outcomes of those chapters are shown beside them. From the scientific community point of view, I think the simulator itself would be of interest. I can think of ways where it can be made more user-friendly by adding a bit more layers publicly available along with the requisite documentation. But I'm just not sure whether it would be possible for me to achieve that by 31st of July, which is the thesis submission deadline. So I will focus on the chapters first and maybe prioritize this a little. But yeah, this is the current status of the thesis.
Comments, questions?
Just one question, please. So the chapter
Geometry characterization.
geometry characterization.
That is the work which was done slightly towards the later.
Can you go back to the slides so that I can understand the scope of the chapter? I have a question.
Spherical and comparison, I think this would also go into. Comparison, it's an extreme trying to derive its parameters. It's quite rich in its promise, but I would have to try to make it as sound and solid as possible while writing the thesis.
So in the previous group, that the first professor changing and increasing the polar temperature, how far are you going? What is the increase in the polar temperature? You start with 1 kilometer substitution.
Go from 0 to 100. So coverage, 0% coverage to 100% coverage, fully covered. Yes. But the reason I mentioned they don't really flatten out completely, the lighter curves, we had expected them to flatten, but they probably don't because of the because you're still using a beaming function, which is why on the right, if you see, once I use an isotropic injection, which is what we think of intuitively, they flatten out.
You have to write this part.
I will try to complete it in the next week, frankly speaking. But that is my priority for the time being, to be able to have something in a reasonable shape. My this thing was also bothering me because once I thought of how to implement gravitational redshift very decently, but that might bring in a slight. I mean, I would be able to improve upon some of the comparison part, for example. Like the more I do, the more I can think of. But for the time being, I think I'll just focus on trying to get this procedure down as solid and soundly as possible.
Dipankar, can you hear?
Yeah, I can hear.
Yeah, any comments, suggestions?
No, first of all, does the thesis as written highlight what are the really new contributions that this thesis is making compared to what is available in the literature? I think it would be useful to pick that up and highlight it for for a reader who is not quite familiar with the literature. So
I've tried to highlight that in the synopsis chapter wise, and in the abstract I've tried to mention that, but there's only so much I can do with the abstract. But the synopsis, the way I've written it so far, focuses on what is the new thing which is done in every single chapter and how it is comprehensive, how we have tried to make it as comprehensive as possible. So it addresses these two things. They're available in the thesis file which has been shared with you. So.
Yeah. Okay. Right. And in the towards the end of the thesis, you have included the Gaunt factor calculations. You have included the steps for polarization radiative transfer. Now, however, there are no results from it. So, what is the argument that you give to actually include those parts in the work that you're presenting?
So that was the reason I think why the scope was shifted to the first 6 chapters. So there would be some tangible results to show. Like I mentioned,
Yes.
the polarization, although it is currently relevant, getting to a point where I have results to show from such a sizable undertaking would be slightly difficult within this time scale. I've tried to emphasize the fact that the algorithms are what I have tried to put forth from my side with the mathematical calculations and the computational details. But I also mentioned in the abstract that this chapter serves more as a proof of concept. So, and the focus of the thesis, if while mentioning the abstract or the synopsis, it doesn't focus on that part specifically. And everywhere it mentions that that chapter is only included to take the current research trend into consideration and put the work in the present perspective. So it's not like we're choosing to be ignorant about that. So whatever polarization, some results have been obtained in the thesis. How they can be extended to polarization resolve using first principles radiative transfer approach. The algorithms are something which have been originally put forth from my side. I mean the individual steps. So I'm first of all not sure about those as well. But I've tried to outline them in as much detail as possible from my side. But you're right, I don't see any results in there for that's a sizable undertaking.
Fair enough. And since you're concentrating more on the pulse profile modeling, you have only one pulsar for which the observational data has been compared. Was there any idea of doing it for any other pulsar?
Yes, initially we had thought of, I mean, there are several pulse profiles commonly available, so I had intended to do it for that. For the time being, I've mentioned it that this can be easily extended to other pulse profiles as well, but the individual exercise with Centaurus X3, rather than just matching the pulse profile and seeing how the profiles, look next to each other, that exercise itself was taken forward to try to make it more insightful as possible to probe the individual pulsar with the chapter which I'm yet to write. Frankly, it's quite intensive. So to beat that exercise to death, we followed up the Centaurus X3 path. But I've mentioned somewhere that this can be done with other pulsars as well. In fact, this approach can also show the promise that it can hold while performing this exercise for other pulsars too, possibly. But rather than just having like a democratic pulse profile list, for the time being, I've just done it for one model pulsar and tried to do it in as depth as possible.
All right, thank you. I don't have any further questions.
Okay, there are no questions. Let's stand. Thank you, Dipankar.
Thank you, Gulab. Is there anything further that needs to be done now?
Okay, we'll plan to chat, but today may not be possible for me, but we'll find the time.
Okay, sure. Okay then. Yeah.
Okay,
Thank
bye.
you. Bye.
So, this is for the RSP content, or we just wait for
Right.
We're going on the last week of July.
last week of July and the first week of August. But most likely the
I
first
can't
week
go
of
into
August.
first week of August.
I'm tomorrow. But I have
How long will you be?
22nd.
Come back 22nd. I might most likely leave on the 31st. I'm not sure.
Oh.
I will book my flights yet.
But then that is
I will know that you will still be available now. I in Korea.
Yeah,
I
yeah.
not be available at all.
That's
Try to
right.
get your timings.
so from today to 31st, you are not anytime.
So I might, so I'm not, so this is Kolkata till the 7 morning.
Yeah. All right.
I have not decided whether I go or
Cancel that.
I have to cancel that.
Yeah.
So I'm not completely sure, but most likely I'm leaving on the 31st, right after our APC. APC on 30th. So leave on the 31st, come back in the second week to organize.
Okay.
But for you, I need to put a signature in your thesis.
That's right.
So moving one side, finalize my travel schedules. And then I'll also get to know from you what is your status. All the best. Which is the contract. Has to hold it at.
Yeah.
Contract.
That's not fair.
And also, I think it's a good idea to put that outline for the polarization calculation.
See, the question Deepankar asked you right now, you also face this. So, one thing that you could have responded to was this non-factor calculations that you've done. They have been done at much higher tuning and resolutions.
I will just highlight.
Yeah. So, what you have presented is an algorithm from your side.
No, the concept
Not a non-factor algorithm for the polarized transfer, etc. There are individual components in that which you have worked on, and non-factor is one of them. So, that is an outcome of the thesis.
separated bond factor out as a separate chapter.
I understand, but that is one of the outcomes of this thesis. So if somebody asks you what is the result, so calculating the contact into understand how to package your things. It's not that there are zero results.
Chapter 6 is a result of chapter 7.
What is chapter? I don't know the sequence.
I've dedicated a whole chapter to bond factor
That's okay. That's okay.
and then
I think we given that
the other chapter dedicated to X-ray polarization.
Contractor you have done, why would you go over it? You did it because it would be, you just done 70% contract. But that's okay. That even a higher bin chart of bond factors is useful for some calculation. Whether it's useful for the polarization or something else, that's a different issue. You can put that as a result of the thesis, which is an outcome, whatever the outcome is. Good. I will let you know my travel dates.
पता नहीं उसको देखो कुछ काट सकते
Okay.
Yes, here, artificial facilities, existing facilities.